Part A of this problem asks us to find the final angular speed of the bullet once it hits the tire. Like always, we should try to visualize the problem before trying to solve it. So let us do that. So what's happening is that our bullet is going to come here and it's going to hit the tire somewhere over here. The tire is going to start rotating and this bullet is going to stick to the tire and go along with it as it rotates. So again, we want to find the final angular speed, and usually for that, probably a good method to do it is momentum. Or since they're asking for angular speed over here, we would probably want to use conservation of angular momentum. Conservation of momentum states that our initial angular momentum is going to be equal to the final angular momentum. So the initial angular momentum is going to be given by the angular momentum of our tire plus the angular momentum of our bullet. So the angular momentum of the tire is 0, and the angular momentum of an object moving in a straight line in general is going to be mvr sine theta. So notice over here that our angle is going to be 180 minus theta. So we are going to get our angular momentum of our bullet is mvr sine 180 minus theta. And we know from our trig identities that sine 180 minus theta is just sine of theta. So this is going to become mvr sine theta. Our final angular momentum is just going to be that this tire is now going to be rotating and we have the bullet stuck onto it. So that's going to be our moment of inertia times the angular speed of the tire. Now, let us think about what our moment of inertia is. Initially, since this is just a, as stated in the question, we can assume that our mass is all concentrated at the rim. So we can treat the tire just like a point particle. So it's going to have a moment of inertia of m times r squared. After our bullet will stick onto it, we also need to add the moment of inertia of the bullet. That is also a point particle, so that will also be equal to m0 r squared. Now these two have to be equal, so we have mvr sine theta is equal to mr squared plus m0 r squared times omega. And finally, we can solve for omega by dividing this term on both the sides to get omega is equal to mvr sine theta divided by capital mr squared plus m0 r squared. Another method to solve this problem is by using conservation of linear momentum. So if I draw our diagram, we see that our momentum of our bullet is going to look something like this. And what we can do is we can split this up into components, tangential, and in both the tangential and the radial direction. We know that this angle is theta. So this component is going to be mv sine theta. This component is going to be mv cosine theta. The component that's producing the torque and which is actually causing our wheel to rotate is this one, which is mv sine theta. So we can use our conservation of linear momentum. mv sine theta is our initial momentum of this object, and that is going to be equal to our final momentum, which is the momentum of this whole sphere, of the tire. So the total mass is going to be capital M plus M. and our rotation, our tangential velocity is going to be given by v tangential. We know that in this case, v tangential can be written as the radius times omega. So we're substituting that in, we get mv sine theta is equal to capital M plus M r omega. And solving for omega, we get omega is equal to mv sine theta divided by r into m plus m, which, as you can see, is same answer we got here. Part B of this question asks us to find the ratio between our final kinetic energy to our initial kinetic energy. So let us just go ahead and evaluate them. So our initial kinetic energy is, we see that our tire over here is at rest, so it has zero kinetic energy, and our bullet is the one which is moving, so it's going to have a kinetic energy of 1/2 m0 v0 squared. Our final kinetic energy, we see that what's going to happen is that our tire plus the bullet is now rotating, so it's going to have a rotational kinetic energy of 1/2 I omega squared. So our ratio, Kf to Ki, is going to be equal to 1/2 I omega squared divided by 1/2 m0 v0 squared, which is equal to I omega squared over m0 v0 squared. So now recall what our moment of inertia was for this one. It was m0 plus capital M times r squared. And we have our omega down here, so we can substitute that. We get r squared times m0 plus m we get our final answer of m0 sine squared theta divided by m0